Well, hello everyone. We're going to get underway. Really great to have you with us. If nothing else, you'll help keep Mike awake after flying in from the UK yesterday. For those who don't know Mike's a joint director of the UK National Climate Science Partnership, which is a relatively new thing in the UK, linking the activity of 7 UK research institutes to develop and deliver climate solutions to government and stakeholders. And so part of his work, he was saying, is trying to work out or help government work out what they need. His own research centres around ocean circulation and climate, based at the British Antarctic Survey in Cambridge in the UK. And he's also a professorial fellow in oceanography at the University of Cambridge. I won't read through the rest of the bio for now. Mike's here primarily for the ACEAS Research Forum. Wednesday and Friday this week, he'll be giving a keynote during that time. But he asked if he could talk about some of this really very interesting work that he's been doing on tsunamis and iceberg calving. So we'll hand it over to you, Mike. Thanks so much for being here, and take it away.
Okay, thank you very much. And thank you for coming along this morning. It's a great pleasure to be here. As Matt said, I'm afraid, horribly jet lagged, so this might not be the best talk you've ever been to this week or even today. It's not uncommon for people to fall asleep in my talks, but if I fall asleep in my talk, then apologies in advance and just tiptoe out quietly and let me have a snooze. That would be great. So this is what I'm talking about. The picture here is the actual field location where we made the measurements I'm going to be talking about. It's a stunningly beautiful place. So if you take nothing away from this talk, just admire the scenery and what a fantastic place is. And if you've never been there, then go, and I'll show you some more photos in a moment. It's very collaborative work. The photo here is just the field team from the measurements that we made. This is when we called into the South Korean base on the Antarctic Peninsula. That's me there, just proving that I do get my hands dirty and wet sometimes. But there's a whole load of collaborators that I've listed here that have contributed to the science. None of them are here, so I'm not going to read their names out and just going to pretend they don't exist and that I did everything and that all the good stuff was from me. So this is the structure of the talk, just a bit of context, then some detail on what we did and what we found and why we think it matters. And then wrapping up. It is quite a narrative kind of presentation in that it's a lot of we went here, we did this, we went here, we did this, that sort of stuff. But it all hopefully comes together at the end with why we think it matters. So in terms of context, this is an area that you're all very familiar with. And I realize I'm talking to a group of experts on Antarctica, so I don't need to go into much detail. But the area we're really interested in is the shallow waters on the shelves around the Antarctic continent. Most of the work I've done down the years have been in the deep ocean. Here we're looking at the shelf seas, but they are still very important for reasons that you know, to do with glacial stability, ice sheet deflation and sea level rise, but also ecosystems, carbon drawdown, dense water production, all these sorts of things. Don't need to belabor the point. And we're really interested in mixing on the shelves. And what I did was draw a cartoon to try and summarize why we're interested in mixing on the shelves. And my graphic skills are extremely poor, so apologies for the qualities of this, but it's the best I could do. But the reasons we're interested in mixing are things such as the upward flux of heat from deep layers into the shallow layers of the ocean, and what that means for sea surface temperature, what that means for sea ice production, sea ice melt, depending on the time of year. Also, the upward flux of nutrients into the euphotic zone, so supply of macronutrients, possibly micronutrients from the sediments into the sunlit zone, where they can support productivity of the ocean. The rate and pattern of glacial melt depends on mixing, because if you move the water around, you move the heat around, that can impact the glaciers and the ice shelves in different places and in different ways, and that can contribute to destabilizing glaciers in some circumstances. And in some parts of the world, mixing is very important for dense water production. That's in typically the cold parts of Antarctica, such as the Ross Sea, Weddell Sea, and so on. Not really the Antarctic Peninsula, where the work I've been doing is from, but perhaps the results translate somewhat. Just an example of one of the impacts. This is a composite of chlorophyll in the Southern Ocean. It's low around lots of regions of the Southern Ocean for well-known reasons, but then you do have some hotspots of high chlorophyll, and one of those is the shelf of Antarctica. Obviously, that's where a lot of nutrients get injected into the ocean, and mixing obviously is key in making those nutrients available for the plankton to grow and increase chlorophyll. So what causes the mixing? Again, apologies for the graphics. We know what causes the mixing. We've known about it for decades, longer. Wind. If you've been to the Southern Ocean, you know it's windy a lot of the time. That mixes the ocean. Tides and anything that drags water backwards and forwards across topography causes mixing. Buoyancy forcing, heat loss at the surface, especially in winter, that causes mixing. If you get deep plumes, convective plumes, and obviously brine rejection is coupled to that as well. So none of that is new. We know what causes mixing. But as always, there's many unknown these things. No substitute for field work. I have to say that as an observational oceanographer. So what we did, and this is a few years ago now, was we took the Bass research vessel, as was the James Clark Ross, to the Antarctic Peninsula, and we had funding for 3 sets of field work in 3 different places. It was a very interdisciplinary set of cruises. We were looking at glacial retreat and what the impacts of that is. We were looking at the colonization of newly exposed seabed by benthic animals. So when glaciers retreat, they expose parts of the shallow seas that's then available for animals to move into. We were looking at the disturbance of benthic communities by iceberg. We're looking at blue carbon, so what all this means for drawing down of carbon from the atmosphere and modulating climate change potentially. So it's a big team, big multidisciplinary team on board the ship, and we targeted 3 sites. 1, 2, 3. The really interesting one from today's point of view is this one here in the middle, which is Borgen Bay, and we'll come to that in some detail. So this is zooming in on Borgen Bay now. Borgen Bay is on Anvers Island. So this is Anvers Island here, and it's at this place on the Antarctic Peninsula. The background plot here is from a paper that we published in Science a few years ago, looking at glacial retreats on the peninsula. So the red dots show where glaciers are retreating, and the blue dots show where glaciers are stable, possibly advancing slightly, and the color in the background shows deep ocean temperature, deep here being sort of the depth of the shelf. So you can see the impact that the ocean temperature has on glacial stability. And the reason we chose the sampling sites that we did is because we have these contrasting glacial retreat histories in different places down the peninsula. But this is the really interesting site in Borgen Bay. So to try and give you a little bit of an idea what it's like, this is some drone footage that we recently took. So this was not from the expedition that I'm talking about today. We went back to Borgen Bay this winter just gone on our new research ship, the David Attenborough, and we spent some nice time flying drones around to get pictures of the ship, but also Borgen Bay in the background. The ship is kind of the scale bar here, I suppose. But this is the glacial system in the background that's actually really important for the work. It's a stunningly beautiful place. You can't really see it at its best here because it was winter, so there's very little daylight. We were flying here in just the hour or half an hour of daylight that we had before it got properly dark again. But it is actually a very beautiful place. So what did we do and what did we find? What we did on the expedition that I'm talking about, we did a whole load of measurements, including CTDs. I'm sure you know what they are. Lots of work from small boats. because when you've got a 100-meter long research vessel and you're working in shallow waters, there are places that they're very nervous about taking the ship. And for those, we still want data, so we just used the ribs and went out and collected it in a more manual way. We measured a whole load of physical parameters, also geochemical traces, which are very interesting too, but a different story. And that's what we did. What we found, right. So we've got a temperature section and we've got a salinity section. The glacier is down at this end. The black is obviously the seabed. And this is Borgum Bay bathymetry, and these are sites where we did CTDs, including some very close to the glacier. Some of them were within 100 meters of the glacier, and they were done from the ship, and the captain was not terribly happy most of the time, but he did it, bless him. And the profiles look pretty much like you'd expect them to. So you've got warm water right at the very surface, because this was done in the summertime, this first expedition. You've got a temperature minimum layer, which you often see in the Southern Ocean, and then warmish water at depth, and salinity. Obviously, it's got to be saline at depth, fresher at the surface. It's got to be like that to be statically stable. The temperature minimum layer, often that's winter water in the Southern Ocean. Here, it's more to do with glacial meltwater, because the glacier's here, and the glacier's melting. You get these buoyant plumes rise up the glacier, and they mix as they go, and they reach a level of neutral buoyancy, and then they spread across the bay at that depth. And that depth happens to be somewhere in the sort of 100 meters to 50 meters depth interval. Key point, the stations were not done sequentially. So it isn't a case that we started there and did them in a line, or start there and did them in a line. We were jumping around an awful lot. And the reasons for that is because we had to fit in all the biological sampling, all the benthic sampling, all the camera work to actually look at the benthos. And actually turned out to be extremely useful for us. As a physical oceanographer, that's not the way you want to do it. But luckily, it turned out to be incredibly useful. And I'll explain why in a moment. So what it looks like, this is looking forward from the ship. This is what Borgum Bay looked like when we first got there. The mountains are huge. It was very sunny. It's absolutely stunning. Just to put into scale, the mountains are about 2,000 meters high. The front of the glacier is about 40 meters on average. So you can't really see from this photo because it's two-dimensional, but it's a vast sort of landscape. It's very impressive. A few days later, a lot had changed. The weather had changed, but the thing I'd really like to draw your eye to is that a big chunk of the glacier is now missing. And you can't really see that too well, but if I bring up the first photo, and you keep your eye on the outcrops, look again, you can see a big front. It doesn't line up exactly, but a big front of the glacier is missing. If you don't believe me, you can look at satellite data. You can look at satellite data. This is a satellite image from Landsat just before we got to Borgum Bay. The glacier front of interest is this line here. About a week later, that's the comparable one. And what you can do is draw a squiggly red line along the glacier front. This is the way to do science, isn't it? Drawing squiggly red lines on a satellite image. But you can do that, and then you can bring up the first image again, and then zoom in because it's hard to see, but you can see this strip of glacier front has disappeared. And if you look at the scale bar, that's about 1 kilometer of glacier front carved off the glacier. And you can do some calculations and do it properly, not just drawing squiggly red lines, but you can work out a value of about 3 million tons of ice from above sea level disappeared. Below sea level, there's about 200 meters of ice. We believe a lot of that disappeared as well. So we didn't see the carving event. Well, we did see the carving event. We didn't get good footage of the carving event, unfortunately. However, these carving events happen relatively frequently in Antarctica. So this is just a couple of bits of footage that other people have taken from a research ship of carving events in Antarctica. So this is one from our ship. This is a different ship, different country, different expedition. This event that it shows is actually quite a bit smaller than the event that we saw. but they were quite a bit closer to it. So in some respects, it's actually more dramatic to observe from that perspective. But you can see the ice falling off the glacier front. You see it starting to generate waves in the ocean. These are tsunami waves. They're not the massive ones you get generated by earthquakes, but they are triggered by geophysical events, so they're classified as tsunami waves. You can see more of the glacier collapse once it becomes unstable and starts calving. And still more of it goes into the ocean, and the waves get progressively bigger. And they start rolling towards the ship. I've purposely not included the sound on these clips because you do hear the people sort of narrating. And first of all, it's, wow, that's amazing. And then it's kind of, oh. And so this one is the same event, same ship, but from down on deck level now. And you can see as the waves get closer and closer to the ship. Yeah, so that was quite exciting. Nobody got hurt, but it was quite an event for them. They ended up with big chunks of ice on the deck of the ship. Anyway, so I mentioned just a few moments ago, we went back to Borgum Bay very recently, just a few months ago, and it was winter, so it was mostly dark. And we were looking out of the bridge, and I stood next to Joe, who was the third officer, and telling them about the science, telling them about calving events, telling them about mixing, why we think it matters. But then I was explaining that this is very dominantly a summertime process. That's when the glaciers are least stable, and we're not going to see anything like that happening while we were there in winter. And he was sort of going, okay, that's a shame. And then as I was saying that, this big chunk of ice on the front of the glacier started rising up and calving. This was just taken on Joe's phone. So this was just because he happened to be there with his phone in his pocket that we got any footage of it. But again, the scale of it is vast. This is 40 meters. This is several houses, one on top of the other, of ice that's calving. And this was, this is actually really small compared to the event that we saw way back when. So I felt like a bit of a fool, to be honest. I affirmed everything they did suspected about me. Right. So you can do some fun calculations. So the event that we saw back from the James Clark Ross in 2020, we can actually calculate how much energy was deposited into the ocean, because we know how much ice calved from above sea level. We think most of the ice from below sea level also calved for reasons that I won't go into. And you can calculate how much potential energy was released just from MGH for above sea level and Archimedes theory from below sea level. And you get a value of a minimum of this, 6 times 10 to the 11, if it's all just from above sea level, possibly as much as 2 times 10 to the 12 joules, if everything from below sea level calved as well. And to put that into context, this is about the same amount of energy as 500 tons of TNT exploding. I don't know if you remember a few years ago, there was an awful explosion in Beirut when a fertilizer warehouse exploded. This is a very similar amount of energy to that. And the glaciologists tell me this is kind of average. It's not trivial, but it's not huge. It's kind of, significant, but nothing terrifically unexpected. So you have to think, where did this energy go? I mean, we heard it, so some of it had gone into sound waves, surface waves, certainly directly into heat. But my contention is that a significant amount of it went into mixing. Why do I say that? So temperature sections, these are the same data that I showed you a moment ago. And I made the point of saying that the temperature stations, the CTDs, were not done sequentially. So the top panel here just shows all the data that we collected before the calving event. And then for the bottom panel, I've added in 2 CTDs here marked in blue that were done after the calving event. And you can see even by eye how different these stations are compared to before the event. And in particular, the temperature minimum layer is completely absent now. that's been mixed away completely. So there's been a very strong homogenization of the water column down to 100 meters, actually a bit more. And obviously we contend that that was caused by the calving. Now, we didn't do very many CTDs, but we do know that all of Borgum Bay was affected by the calving. One of the reasons we know that is because we had an ocean thermosalinograph running all the time. So everywhere the ship went, we were measuring temperature and salinity at about 6 meters depth. That was the depth of the intake. So this was before the calving event. This is the data after the calving event, and you can see you've moved from warm to cool at the very near surface layer, and that's consistent with mixing upwards of the colder water from below the surface. You might think, well, you just dumped a whole load of ice into the water, that's going to cool the ocean. Isn't it that you're just seeing? We don't think so. A key point is that before the event, you have this cluster of points. After the event, it actually gets more saline as well as cooler. So if it was ice melt cooling the ocean, it'd get fresher. It's actually got more saline. That's consistent with mixing upwards of more saline waters from below. And it's over the whole scale of the bay, which is, quite a few kilometers. In terms of the process, we can actually do some investigations using the ADCP data that we collected. This is profiling ocean currents beneath the hull of the ship, wherever the ship goes. And from that ocean current data, you can calculate things like the shear of the ocean, which is just how different layers in the ocean drag across each other, and also the amount of energy contained in the internal wave field. And you do get some very interesting patterns. These plots look very similar to each other because they're both calculated from the same raw current data, so that's inevitable. But it is quite interesting nonetheless. For the shear, for example, is relatively low until you get to this point, which is the time of the glacier collapse. After this, it spikes up high and it stays high for at least a couple of days afterwards. And the same in relation to the energy in the internal wave field. There's a gap in the data. That gap was caused by us turning the ADCP off. And I thought that was a terrible idea. But we did it anyway. The reason we did that was to calibrate one of the other echo sounders, and they needed quiet ocean to do that. And it actually turned out to be extremely fortuitous. And I'll explain why in just a moment. You can see here, this is essentially how much energy there is in the internal wave field in the ocean. It spikes high. There's another peak here, which is interesting, and we don't fully understand. It may be that there was another calving event then. So instead of one calving event, there were sort of multiple events, and that was another one soon after. We weren't within eyeshot of the glacier at that point, so we can't confirm or refute that. But it's still very high. And obviously these waves, these internal waves that we're seeing are internal tsunamis in the same way that the surface waves are surface tsunamis. So this is with the other echo sounder, the one I just mentioned that we calibrated. So this is from an EK80 echo sounder, and this is typically used for mapping krill swarms or quantifying zooplankton biomass, that sort of work. This is just a raw plot from the software that's used to run the echo sounder. What we were doing on this cruise was using this echo sounder to try and trace internal layer movements in the ocean. Because if you reflect sound off suspended sediment or anything else in the ocean, if those layers that contain the reflectors move up and down, then you can see those layers move up and down. And even in the raw data, you can see quite clearly some layer waves internally in the ocean. This is the work from Tobias, who was one of the students we had with us. He has a very nice semi-empirical method for tracking the layers. So instead of just looking at them and confirming they're there, you can actually identify them, which is what these yellow squiggles are here. The glacier calving event is this red line. You can see there were internal waves in the ocean. There's always internal waves in the ocean. But then there's an awful lot of noise. And then afterwards, you see these big, much bigger internal waves propagating. And I thought this was remarkable. I actually just thought, we're actually seeing beneath the ship in real time, not just the internal wave going up and down, but seeing actually how it's enhanced by a glacial calving event. And you can calculate the spectrum, power spectra of these waves. You look between F and N for internal waves, and before is blue and afterwards is red. And you can see there's a big increase in energy, as you would expect. So I thought that was quite impressive. Now, the amount of data we had is limited, inevitably, especially because it wasn't supposed to be what we were looking at. It just kind of happened. So what we did was some numerical modeling to try and get more idea about the dynamics and to look at how sensitive these sorts of processes are. This was done by my colleague Dave Munday at BAS. The domain here is about 10 kilometers in the X direction, a few hundred meters in the vertical, and the glacier here is at the right-hand side, and its temperature and salinity, and it's completely stagnant. There's no forcing on here at all, so it's a completely quiescent ocean. But then what Dave does is introduce waves on the right-hand side to simulate the glacial calving events. And you see the waves propagate extremely rapidly across the whole bay. They interact with the bathymetry very strongly. You can even see overturns where they hit this ridge. This is realistic bathymetry, by the way, and the small scale patterns where the overturns happen and lead to turbulence and mixing. This version has got a hard boundary here, so we're reflecting the waves back into the domain. That's not realistic, but neither would it be realistic to allow all the waves to propagate outwards because it's a semi-enclosed bay. This is one of the issues you have when you do this in 2 dimensions, is you can't make it realistic. But nevertheless, it's extremely beautiful, and it tells us a lot about how this actually works. Some of the things are intuitive. Bigger waves give stronger mixing. Scattering of the topography matters a lot, it seems. The ridge in the middle of the bay is clearly very important for a key site for where the mixing actually happens. And the fact that we saw the internal wave energy enhanced in the bay for at least 2 days afterwards tells us, we think, a lot of the energy is being reflected back from the side, even though some of it leaks out from the bay and across the broader shelf. So why does this matter? So taking a bit of a broader view, calving events of this scale are not isolated, either in space or time. This is the calving history of the glacier in Borgum Bay, going back to 1955. It's retreated several kilometers up to present day, and a lot of that retreat is associated with calving. But even a stable glacier calves or can calve, so it doesn't have to be a retreating glacier to exhibit calving. We think the only unusual thing about the event that we saw is that we were there to see it. In reality, we think it happens pretty frequently. We say that based on satellite information. This is from my colleague Ben Wallace, who uses synthetic aperture radar data to track glacial calving fronts. This is the calving front in Borgum Bay going back to 2015. The red markers show calving events that are as big as the one that we saw, and that is the one that we saw there. That big retreat of the glacier was the calving event that we saw. The blue markers show events that are at least half the size of that event, and obviously half the size is still very significant. So you're getting several events per year, and some of them are actually quite a lot bigger even than the one that we saw. So again, what we saw was dramatic when you see it, and it certainly had an impact on the ocean, but it wasn't atypical. Now that's just one location. You think about all of Antarctica, about 3/4 of Antarctica is floating ice shelves. They are probably not that relevant for this story because the ice is already afloat. And when they calve, you can get big icebergs that will float. Where that potential energy eventually goes into the ocean depends on what happens to the icebergs. However, Aside from those ice shelves, there's still something like 3,000 other marine terminating glaciers that are grounded, and so behave probably quite similar to the one that we were looking at if they have active calving fronts. There's more than 800 glaciers on the Antarctic Peninsula alone. This is the same plot I showed you previously. A lot of them are retreating, and the retreat rates are accelerating. That's hinting that this could be an increasing process. This could be a strengthening process because of the climatic change we're seeing in the cryosphere at the peninsula. Thinking more broadly still, this is the distribution of glaciers in the world, stolen from NSIDC website. Some of them are not marine terminating, like the Himalayas, so probably not relevant. Antarctica has quite a few, especially peninsula, but there's an awful lot of other ones. Greenland, Svalbard, Alaska, Canada, Patagonia, they've all got marine terminating glaciers that calve. So this process could be happening across quite a large area of the world. Now, since we did this work and published this work, other people have been examining similar things. There's a couple of nice papers have appeared just this year. One with using fiber optics in a Greenland field, another one using more conventional ocean measurement systems. But these both found internal waves in the ocean in response to glacial calving events. They're quite a bit smaller, the calving events that they saw, and it doesn't seem that these propagated as far as the one that we saw. But it does, I think, give some evidence that what we saw is not just an isolated one-off event, but is probably happening in a number of places, certainly Greenland as well. Why does this matter? Well, I sort of hinted at a moment ago. We know that we live in a warming planet. The polar regions are warming more than the rest of the world. Calving is likely to become more frequent, or could well become more frequent, because of the change in air temperature and especially the change in ocean temperature for Antarctica. This is from the IPCC report we did a few years ago. Glacial mass loss here, even under a low emissions scenario, is going to go up over the course of this century. This is for all glaciers, but it includes marine terminating glaciers. It's very possible that this process will get stronger over time as calving increases. However, as glaciers retreat and retreat, they will eventually pull back onto land. And that's what we're seeing in some parts of the Antarctic Peninsula already. Once that happens, this source of mixing will just be shut off, because the calving, as happens, won't be putting potential energy directly into the ocean. And so you could get this very interesting pattern of an enhancement of mixing and then a diminution of mixing that's spatially structured, but is likely to play out over sort of decadal to centennial timescales, which are obviously the timescales of climate change. And this will impact everything that we discussed at the start, including stratification and sea ice production, nutrients, and so on. So just a few thoughts to wrap up. The talk was really about mixing. This is the same plot I showed a moment ago. And what I hope I've convinced you is that there was an important process, potentially important process, missing from this plot, in that glacial calving and enhancement of the internal wave field wasn't there. And I've crossed out the word Antarctic because I think this is actually applicable to other glaciated regions as well. We wrote the paper a few years ago, came out in Science Advances, and there's a little media flurry when that happened, and I was invited onto Sky News, which is a national news channel in the UK, and interviewed by Kay Burley, who's a bit of a UK legend. She's retired now, but she loves savaging politicians, so it was quite intimidating. I don't think she knew what to make of me, to be honest. She was asking some very strange questions, but it wasn't, getting oceanic internal waves on national news has to be a career high, right? So that was a good thing. That was a good thing. Sky News. Quality. BBC didn't touch it, so there you go. That tells you all you need to know, probably. But so what next? Well, as most science seems to be, this actually raised more questions than it answered. There's huge numbers of unknowns about this, including what are the key controls on tsunami formation and the different forms of calving, so above sea level or below sea level or hybrid. How do they spread under different conditions of stratification? How far do they spread? I mean, we saw them go for many kilometers. If they go for many tens of kilometers, then quite a large amount of the shelf could be impacted. What's their net impact on things that we care about? How do we represent them in models? How are they changing over time? Do they represent a positive or negative feedback on the cryosphere? We don't even know the answer to that. So what we did was write a proposal to the lovely people at the Natural Environment Research Council and asked them for £3.7 million, and they gave it to us, which is wonderful. So we have this new program called Polar Ocean Mixing by Internal Tsunamis, which spells polo mints. I don't know if that means anything in Australia. In the UK, it's a little sweet with a hole in the middle. So anyway, and these are the people involved. The central goal is to actually, in essence, go back and do this science in a systematic way instead of a serendipitous way, to try and find out what are the key mechanisms, how do they vary over time, what are the net impacts, and so on. Schematic for how we're going to do it. We're going to use the ship, but in quite a minor way, because this isn't the sort of science that necessarily is best done from ships, although they are still incredibly useful. A lot of small boat sampling, remotely piloted aircraft, lots of ocean glider work, physical biogeochemical moorings. And the idea is to have a sustained presence in front of a glacier for 2 full years, including the winters, so we can capture a whole spectrum of calving events, large and small, different formats, different stratification conditions, and actually measure what impact they have on the ocean as a function of time. It involves remote stereo camera systems, microstructure profilers, and everything in the kitchen sink. We're going to do it close to Rothera, which is the site of one of the British bases in Antarctica. The Sheldon Glacier is very close to Rothera. It has calving characteristics very similar to the glacier in Bourbon Bay. So we're confident we'll get lots of calving events over this 2-year window. These are the places where we're deploying equipment. We're also doing some modeling on different spatial scales, very fine scales with MIT GCM, to try and understand the dynamics in 3D, not just 2D. But then a sort of regional scale model with Nemo Medusa on this sort of shelf scale, where we can embed what we learned from the observations and the fine scale modeling in terms of a parameterization. And then the idea is to deploy that in a fully circumpolar 12th degree Nemo Medusa model run. And then we can do the runs with the tsunamis absent, present, doubled, just see what it happens. We can do all the experiments that we want to do to try and understand how this might change in future under different climatic states. The observations haven't started yet. They start next month, and especially into January. The modeling can go on ahead. So again, this is from Dave Munday and also Neil Fraser at SAMS. Rothera is here. This is the model domain. These are actually surface tsunamis now. The 3 different panels throw 3 different sites of glacial calving, and this is just the surface wave fields associated with those carvings. But you can see how the waves propagate outwards from the calving sites. Internal waves are coming next. This is just the surface waves so far, but already is very beautiful. The deep channel is here. These are shallow islands, but you can see the deep channel here. This is likely to be where the internal waves come out. We're very interested in the reflections and how different bays keep the energy within them, and also how much energy gets across into the open shelf regions and can have a bigger footprint spatially. So, summary, wrapping up, internal tsunamis triggered by calving events represent a previously underappreciated source of mixing for Antarctic shelf seas. I did actually Google the term internal tsunami when I was writing the paper. I thought this is going to be a new term. Fantastic. And Matt Alford from Scripps had used it. One paper, but he found internal tsunamis in a lake from a landslide event, and so he beat me to it. Anyway, I'm not bitter, but anyway, there we go. Internal tsunamis are super cute. They are absolutely gorgeous features, and they are possibly important. I believe they have relevance beyond Antarctica, and they're probably evolving on climatic timescales, but how, we don't know. We're working to ascertain how they work, what they do, what the feedbacks are, and so on. They're probably present in quite a lot of historical data sets, especially moorings data with high temporal resolution, but probably weren't spotted at the time, largely because no one was looking for them. So if you have any moorings data going back over years or decades with unexplained spikes in them, it would be very interesting to look at, see if there were any glaciers nearby that calved. And there's far more work to do than we can do, so partnerships are very welcome. And that's it. I'll stop there. Thank you for your attention.
Well, thank you, Mike. Yeah, it was really interesting. I think Mike would welcome your questions, strange or otherwise, about this topic. I will keep an eye on the online. I'll do my best. If you're online, there's about 30 or 40 people online, Mike. Any questions? Alex, I think I need to run a microphone to you. Is that right?
Thanks, Matt. Thanks, Mike. Really interesting talk. I'm wondering if this can be one of the rare near coastal sources of waves that might impact fast ice, causing breakouts or that kind of thing. Have you thought about that aspect?
It could well do. I mean, we've thought about it. We don't have evidence necessarily, but it could do. When I was first looking at this, I thought this would be like a summertime process, really. And my naive conception was just that everything freezes up in winter. There's no calving, fast ice, across the ocean, and then it just waits for spring, and then things start happening again. But from the satellite data, you can, and we saw it in person, but from the satellite data, you do still get calving events in winter. They're just less frequent. And I think that, were you to get a calving event in front of fast ice, you'd break up the fast ice, obviously, that the ice hits, but then the surface tsunamis could well disrupt the fast ice as well. So it makes perfect logical sense that it would.
Possibly another feedback if you start breaking up fast ice, making more fetch for wind waves to form. Yep.
Exactly.
Thank you.
You're making me work for my lunch today.
No, there's one right at the back.
I think I saw that.
Thanks for that, Mike. You had a storm the night that the cliff fell off, and you didn't talk about the winds or wind variations as a contributor to those internal tsunamis. Do you want to tell us the difference between those two and why you could eliminate the winds?
The winds weren't that extreme. It's a fairly sheltered area. The weather changed, but we didn't get a particularly massive storm. It just sort of closed in a bit. We did look at the wind data. We were measuring winds everywhere that the ship goes, just as you do. And it did get a bit stronger. And we didn't have a quick look at how much energy was coming from the winds. And it was relatively small. And I think what that actually sent us down the road of was looking at, well, what's the most effective way of generating internal waves in the ocean anyway? And winds can do that, but we don't think that was what we were seeing. We actually think that potentially the most efficient way of generating these internal waves is when you have calving events that include ice from beneath the sea level. So you've got 40 meters above sea level, 200 meters below. If you carve the ice from beneath the surface, you can put that energy directly on the picnic line. So you don't even have to propagate energy down from the surface to the picnic line in order to generate internal waves, because you're right there. And that's actually quite unique, because I don't need to tell you this, Nathan. In the ocean in general, getting energy into the interior is one of the big, for example, dimes on a much bigger scale. That was one of the really key questions, was how do you mix the ocean interior? You either get energy down from the surface or up from the seabed, or from the lateral boundary. And here we think it's the lateral boundary being active that's particularly efficient at driving the internal waves.
Thank you.
He sounds convinced.
No, he's not. He's going, no. Rubbish.
Back in the early 2000s, there was a big tsunami in Indonesia. And there was at least one paper I remember that showed the tsunami wave reaching the Ross ice shelf and causing calving events there. Yeah. This brings me to more local calving events. And on a small bay with so many, or more than one terminating glacier, how big the calving event has to be so that wave affects other glaciers and causes more calving events?
How big, I don't know, but I think it's probably a genuine process. And some of the work that's coming out of the Greenland gang at the moment is really interesting, in that the calving events that they see, they homogenize the ocean, they mix up heat, and they're actually seeing it as a direct feedback on the glacier that the ice calved from. I mean, any other glacier nearby, if the waves propagate and they cause mixing there, then they would be impacted too. But they're seeing this as a positive feedback on the calving by mixing heat up to destabilize the glacier further. One of the things that they saw, which I thought was really beautiful, one of their upward-looking ADCPs, they had a rising bit of carved ice go through the beams of the ADCP. So they could look at the water being entrained behind it and dragged up as the ice rose. And this is, relatively warm water that's being dragged up really close to a glacier. So they're seeing it as a positive local feedback on glacial stability. But if the waves propagate for many kilometers, there's other glaciers nearby, it makes sense that they would be destabilized as well. But it comes back to the key question of how far do these waves actually propagate? And that's one of the things that at the moment we really don't know, and we need to know more about.
So there are other processes causing mixing as well, right? So I just wondering, could you comment on the relative importance of this process? What's the other process, like in particular the tidal mixing?
Yeah. So we did some calculations, and when I say we, I mean Mark Innell from SANS did some calculations, and we put them in the paper in Science Advances. This process, if you take if you look at like an instantaneous calving event, and look over like a few days when the waves from that were still active, this process just dominates everything. It's much more important than winds. It's much more important than tides. Much more important than buoyancy forcing. But of course, these are sporadic events. These are sort of quasi-random events. So you have to say, well, does this actually matter quantitatively over the course of a summer season or over the course of a year? So we did some calculations using typical Antarctic Peninsula values. So how well they translate to other regions, we don't know. But for the area that we were working, what we found was you only need something like 2 events per year for this to be much more important than tides and roughly equivalent to winds in terms of mixing, in a quantitative sense. Yeah. But a key thing to note is this is very different. Winds and tides happen pretty much all the time. buoyancy forcing happens very strongly in winter, a little bit in summer, very strongly in winter. And this actually just puts bursts of strong mixing into the ocean when it happens. So instead of just being a sort of continuous distributed process, this is just, if you think about Antarctica as a whole, this is just like putting bursts of mixing in. It happens every day somewhere, but little bursts of mixing everywhere, somewhere around Antarctica. So the key question is, what does that integrate up to? And that's what we're trying to answer with the new project, because from the calculation we did, we think it's important, but yeah, exactly numbers on that, we don't know.
So, Mike, we've got a question from Nerily Abram online. So she's asking, do you think the mixing effect would be different in East Antarctica compared to the peninsula?
Great question. Intuitively, I would say yes, in a net sense, because my understanding is that there's fewer of these sorts of glaciers in East Antarctica than there are at the peninsula. So I suspect it's more significant at the peninsula just because there's a lot more of it. But I think when it does happen in East Antarctica, in one of the marine terminating glaciers there, it could well have a similar sort of impact in terms of homogenizing the ocean to the one that we saw. So it's probably rarer, but it's probably important when it does happen, I would say.
Thank you. How does this compare to the mixing, for example, to like normal sense tsunamis, so the ones that are due to a land kind of change in Earth crust?
I suspect, I mean, for an earthquake or a landslide or something like that, I think the tsunamis generated by those are enormous compared to what we see here. But they're thankfully very rare, you know, big earthquake-driven tsunamis that threaten populations and villages and so on. So I think those would have a much stronger impact in terms of mixing the ocean. The difference is, you know, this is happening somewhere in Antarctica all the time. There'll be events happening today like this somewhere in Antarctica. So in an integrated sense, which one matters the most? Probably this one, especially for, you know, the Antarctic processes that we're studying.
Yeah. Can I ask another question? So I've got one more question. That was actually what I thought about first. So how difficult would it be to kind of like create a historical data set? You sort of mentioned it already a little bit, on kind of see what the observations that we have from like seals, moorings, all that, and sort of like satellite imagery where you kind of draw the kind of calving line, and then sort of like kind of see if that sort of matches up all the time.
Yeah. So that's some of the work that we're doing in the new project with the synthetic aperture radar satellite data. The group from Leeds, Ben Wallace and Anna Hogg, they've got all the data. Previously, they've mapped out the calving fronts in a very sort of labor-intensive way. They're applying machine learning techniques to those data now to try and create a data set for all of Antarctica of the calving histories of the marine terminating glaciers. And then we're going to try and couple that with historical ocean data. Things like seal tag data probably don't lend themselves very well to this sort of study because the seals move very rapidly, so you get in the sort of spatial temporal aliasing problem that you always get. And things like ship-based CTDs, you know, we happen to be in the right place at the right time to measure, you know, before, during, and after, but that's actually very rare. It's likely to be ocean moorings data that capture these events better. So one of the places we're going to put a lot of emphasis is looking at historical moorings records, and particularly, you know, unexplained blips and spikes in the moorings to try and see if they line up with the satellite data.
Great. We'll go one last one to Jan, and then we'll wrap up.
Thank you, Mike. It's more a comment than a question regarding the wintertime carving of ice shelves and icebergs. I've just watched the Dalk Glacier which is I'm not sure if it's a marine terminating glacier, but it has a whole lot of fast ice in front of it. So I can actually see that the glacier front retreated, but now we have glacial debris on the fast ice. So it didn't obviously induce a surface wave. But if you think about if that happened underneath as well, it could be another internal wave. So yes, calving happens in winter. It's just my 2 cents to this.
Okay, I'm glad to hear you say that. I'm reassured I'm not going completely mad. So.
Cheers.
Well, thanks so much, everyone, for coming, and thank you very much for to Mike for volunteering for the seminar. I think it was tremendously interesting, and we'll thank Mike one more time.
Thank you.